Alright, this video is going to be a continuation of the curve sketching notes, and this is specifically for sketching the curve with the trig function because these can be a little bit more complicated. So the equation that we're going to look at is 2 cos x plus 2 sine x cos x. And we are going to draw this function on the interval from 0 to 2 pi. So that's the domain of the function. I don't want to look at any other x values than what I have there. So first, I'm going to look at the information that I can find from the original function. And I can find x-intercepts and y-intercepts. And so to find x-intercepts, that means the y value needs to be 0. And just like when we solve polynomial functions or rational functions, factoring the problem is going to be a pretty typical way for us to solve this. So if you look here, you can see that there's a GCF of 2, and there's also a GCF of cos x because that's in both of the terms. So when I factor out that GCF, I get 1 plus sine x. And if we were to think of this in terms of like what we would have for a polynomial function, if this in the front said 2x, then you would say, oh, x equals 0. So we're going to say cos x equals 0. And here, if you had 1 plus x, you would say, oh, x equals -1. And so here, sine x equals -1. So this is where it's a little bit trickier because it is a trig function. So we're going to look at our unit circle. And I want to see where on the unit circle the cos value is 0. So if you were looking on the unit circle to where the x values are 0, and I can see that that happens at pi halves and that happens at 3 pi halves. And then I want to look to see where the y coordinate is -1, so I can see what x should be, where sine x equals -1. And the y coordinate is -1 down here, and that's at 3 pi halves. So that means a couple of these answers are redundant. So that means that for our x-intercept, we have 2 of them on the interval that we're graphing, and one is at pi halves 0, and the other is at 3 pi halves 0. And then for the y-intercept, that process is a little bit easier. We just have to plug 0 in for the x value. So if I use my unit circle to evaluate this, I'm going to say that cos of 0 is 1, so that leaves me with 2 times 1. Sine of 0 is 0, and cos of 0, like I said, is 1. So 2 times 1 is 2. Because this one's being multiplied by 0, that kind of zeroes out, and so our y-intercept is just 2. And then since this function doesn't have anything that would concern me as far as asymptotes go, it's not a fraction, so there's no way that the denominator would be 0, since there is no denominator. For asymptotes, I'm going to say none. The other reason is because this is not a tangent graph. Tangent graphs do have lots of asymptotes in them. I'm not too worried about that with sine and cosine. Okay. So next, we want to look at what we can find from the first derivative. So the first derivative is going to be the derivative of this piece, so that's 2 times negative sine x plus, and then over here we have the product rule. So I've got the first term multiplied by the derivative of the second term plus the second term multiplied by the derivative of the first term. And so that leaves me with -2 sine x minus 2 sine squared x plus 2 cos squared x. And again, our method for solving these is to factor them, and right now this is kind of a difficult thing to do because we have this is sine and cosine, and we're not in a position where we can factor out a GCF like we did before. And so that means I probably want all of this to be in terms of one or the other, and it's going to be easier for us to make this all in terms of sine because that's the more dominant function involved. So at the top of your page, go ahead and write the trig identity sine squared x plus cos squared x equals 1. This is the Pythagorean identity. It's one of the identities you used a lot when you did trig proofs. And so we're actually going to use that idea so that we can get rid of this cos down here and get it in terms of sine. So cos squared x is the same as 1 minus sine squared x. So I'm going to go ahead and make that substitution. The stuff in the front is going to stay the same. And then instead of writing cos squared, I'm going to write 1 minus sine squared. And now I want to be able to combine like terms, so I'm going to go ahead and distribute that too. So the front is staying the same. And that leaves me with 2 minus 2 sine squared theta. So at this point, I can go ahead and write this in the correct order and kind of put my like terms together. So squared terms should be written first, and I've got -2 here and -2 there, so that makes -4 sine squared x. And then I'll write -2 sine x next, and then 2. So at this point, this is kind of like a quadratic. It's as though we are factoring -4x squared minus 2x plus 2. That's basically what we have here. So if this is the quadratic that we were factoring, we would definitely take out a GCF of -2 to start with. And then depending on how you like to factor these, you can do like slide divide if you understand what that is. A lot of students don't, or I'm going to go ahead. This one's pretty simple to factor, so I know that 2x times x is going to be how I get that 2x squared. And I know that these last two numbers have to multiply to be -1. And so you only have two options really, +1 and -1, and you can kind of choose where you think they might go. So if I do it this way, I've got 2x squared plus 2x minus 1x, and that works out to be our positive x right there. And then that would multiply to be -1. So this is our factoring, and I'm going to go ahead and put it over here and then put it in terms of sine. So we're going to have 2 sine x minus 1 and sine x plus 1. So if I solve this one, I'm going to get sine x equals 1/2, and here I'm going to get sine x equals -1. And now I'm back to looking at my unit circle to see where the y-coordinate is for each of these things. So the y-coordinate is +1/2 at pi6 and 5 pi 6. And the y-coordinate is -1/2 at 3 pi halves. Sorry, it's at -1, not -1/2. At 3 pi halves, which we've already looked at. And so now we can go ahead and make our sine chart. And I do know I'm going to be cutting the graph off at 0 on this end and 2 pi on that end. So at this point, you can take any of these derivatives to plug your numbers in. And I'm going to go ahead and plug mine in here at the end. So I have to choose a number that's between 0 and pi 6. And pi 6, well, actually, let me check. Pi 6 is the decimal 0.52, so I'll do 0.5. So I'm going to do -2 sine of 0.5 minus 1 times sine of 0.5 plus 1. And I get a positive answer. And then something a little bit bigger than 0.5 would be like 0.6. It was 0.52, I believe. All right, so that's negative. 5 pi 6 is really close to pi, so if I do, I can just plug pi in. Delete that and plug in pi. That gives me a positive. And then 6 is just under 2 pi, so to do the last one, I'll just plug in 6. And that gives me a positive as well. So based off of that, my conclusion is going to be that this is increasing from 0 to pi 6, and from 5 pi 6 to 3 pi halves, and from 3 pi halves to 2 pi. And the decreasing interval is from pi 6 to 5 pi 6. So next we want to look to see if we can see any maximums or minimums, and we can. We are increasing to decreasing, and so that's going to give us a maximum at pi 6. And here is decreasing to increasing, and that is going to give us a minimum at 5 pi 6. And so for us to be able to find those actual points, those are based on the original function. And so I'm going to go back to the original function, and I've got 2 cos of pi 6 plus 2 sine of pi 6 cos of pi 6. And that gives me 2.598, and I'm not going to be able to graph it that accurately, so I'm just going to write 2.6. And then the same thing with 5 pi 6. Oops, I typed too fast. Oh, that's funny. Goodness gracious. Sorry, guys. Oh, I missed one, that's what it was. There we go. Sorry, my phone just went off. Okay, that's negative 2.6. Okay, so that's all the information that we can get from the first derivative. So now we want to go ahead and find the second derivative. And this part is a little bit interesting, especially with trig problems, because your second derivative can be completely different answers depending on which of these forms you use. So for instance, if you're using this first derivative to find your second derivative, then you would use the product rule to find the second derivative. Or if we go up here, if we were using, goodness, this one, we wouldn't want to do that because that'd be like a lot of product rule in there. This one right here, you'd be using the chain rule. And we are not great at doing these with the chain rule, which is why I specifically want to do that one, because I want to practice the chain rule with you guys. I want to kind of review that. So that's what we're going to do. And so I'm going to go ahead and rewrite that problem down here so that I can see what I'm doing. So my first derivative is negative 2 sine of x minus 2, and it was sine squared. And I'm going to go ahead and rewrite it like this, sine of x squared. And that's just so that I can make sure that I do the chain rule correctly. And then plus 2 cos squared, and then I'll go ahead and find my derivative. So my second derivative is negative 2 cos x. And then for this part, I've got to do the chain rule. So negative 2 times 2 makes negative 4. And the inside function is going to stay the same. And I drop the exponent by 1. And then I multiply by the derivative of the inside function. And then I'm going to do the chain rule with this part. So 2 multiplied by 2 is 4. The inside stays the same. And then I multiply by the derivative of the inside. And so just like before, my goal to solve this is going to be to factor it. So I'm going to simplify things. And here, this is negative 4 sine x cos x, and this is negative 4 sine x cos x. Hope you guys can see that. So these are like terms. So I'm going to say this is negative 8 sine x cos x. And the nice thing about this one is we don't really have to do a substitution, it looks like, for this one to be solvable, because we have a GCF of negative 2, and then we also have a GCF of x. So I'm going to take out that negative 2, sorry, not x, cos x. So I'm taking out that negative 2 cos x, and that would leave me with 1 plus 4 sine x. Okay, so let's go ahead and solve this. So we get cos x equals 0 and sine x equals negative 1/4. Sorry, my water bottle's in the way. So now that, I can't look at my unit circle for that, but I can look at my unit circle for this. And so cos, the x coordinate is 0 at pi halves and 3 pi halves. And then here we're going to use our calculator. So we have to be really careful about this, because if I was to think about it, if I'm looking for sine x equals negative 1/4, that would be kind of like asking where's the y coordinate, negative 1/4. And we would know if we were doing negative 1/2, we would have 2 spots where the answer was. So we know that we're going to be looking for 2 answers. And since the answers for these, since we're not going to have exact values, our answers are going to be decimals. The tricky part about this is your calculator, if you solve for x and do sine inverse to plug this in, we would do sine inverse of negative 1/4. Your calculator is only going to give you one answer. And that's because your calculator is programmed to only deal with functions. Actually, you know what? We only need, well, let's go ahead and do 3 decimal places, because we're going to plug this back in. So your calculator, sorry, the fan keeps coming on. So as I was saying, we need this answer to be in 2 different spots on the unit circle. So if you can picture it, this is slightly negative, so this would be kind of like the answer that's over here, and the answer that's over here would be that exact same decimal. It would just be measured, instead of measuring down and measuring the negative version, we would be measuring from 0 to pi, and then we would be adding that little decimal over here. So I'm going to say, I'm going to do pi plus the same decimal that we just had, 0.253. And that's 3.395. And dependent on how much you remember from pre-calc, there is, when you use inverses to solve a trig equation, there are some little shortcuts for that, and I don't remember what you guys, I have no idea what you guys remember from that, but this will work every time, so picturing it like this. So again, my reasoning there was, if I know that I'm looking for negative 1/4 and I can see that negative 1/2 is here and here, then I'm going to expect my answers to be in similar places on the unit circle. And so I pictured that negative 0.253 would be kind of the negative measured angle over here. And so then I said we must have another angle over here that would also be 2.53 down from that line. And since I know this line is worth pi, I just did pi plus those decimals that I figured would be underneath that line. So that was my way of getting those 2 answers. All right, so again, we're going to go ahead and do a sign chart for this. So when I set up my chart, I know that 0 is the end of it, and then I've got pi halves, because that's 0.57, and then I'm going to have 3.394, because that's a little bit more than pi, and then 3 pi halves, and I know I'm going to stop at 2 pi. And the reason I did not use that negative 0.253 is because it's out of our interval. We were not using negative values. Okay, so at this point we are ready to check some of these answers and see what we have. So pi halves, let me just double check. Oh, it's 1.57. Well, I was close. Okay, so I'm going to go ahead and plug in 1, and I think the last version of the second derivative is pretty easy to plug stuff into, so we'll type it in there. So if you plug in 1, you get a negative. And this was 1.57, so I'll go ahead and plug in 2. And that's positive. And then I can plug in 4. Get a negative. And then 6 would be just under 2 pi. Positive there. So that means my graph is concave up from pi halves to 3.4 and from 3 pi halves to 2 pi. My graph is concave down from 0 to pi halves and from 3.4 to 3 pi halves. And I have 2 points of inflection. One is at pi halves. No, it looks like I've got 3. So I've got one at pi halves. I've got one at 3.4. And then the other one is going to show up at 3 pi halves. So those are all values that I want to plug into the original equation. So oh, pi halves and 3 pi halves we've already plugged in. Those are the x-intercepts. So then I just need to plug in 3.4. So 2 cos 3.4 plus 2 sine 3.4 times cos 3.4 is negative 1.4. All right. Now we are ready to graph this on graph paper. I'm fancy, so I've got my little graph paper already set up. So I'm going to go ahead and I've got 12 boxes for pi. And so 1, 2, 3, 4, 5, 6 makes pi halves. And every 2 boxes, pi halves. So that would make this pi 6. And 2 pi 6 is the same as pi thirds, and 3 pi 6 is the same as pi halves, and 4 pi 6 is 2 thirds, and 5 pi 6. And I did those because those are some of the values that showed up when we were working on this. And then after that I think 3, so here's 2 pi over here, and I think 3 pi halves right there in the middle, but I don't think we really need to write these down because we didn't really use those. And then you can kind of scale your y-axis however you want. I know I'm going to have to go a little bit past 2, so I'm going to count 3 boxes and put 1 and 3 boxes and put 2 and call it good. So there's negative 1, negative 2. So I have an x-intercept at pi halves and 3 pi halves. I have a y-intercept at 2. I don't have any asymptotes. I've got a maximum at pi 6, and it's 2.6, 2.33333, 2.66666, so 2.6 would be slightly smaller than that. 5 pi 6, it's going to be at negative 2, right there. I have a point of inflection at 3.4, so 3.4 is just going to be a little bit past pi, and then negative 1.4, so there's negative 1, negative 1.333, so negative 0.4 is going to be right there. All right, so if we look at our concave up and down and our increasing and decreasing, I can see that I'm supposed to increase from 0 to pi 6, and from 0 to pi halves, it's concave down. So 0 to pi halves, it's concave down. And then from pi halves to 3.4, it's concave up. So that's going to hit this. There's our concave up. And then from 3.4 to 3 pi halves, it's concave down. And then to 2 pi, it's concave up. And so there is our graph. And it's always good to know how to plot these on your calculator to check. So what I do is go ahead and type it in. And then what I usually do, and you can see I was already messing with the window, is I try to change my window so it looks exactly like the scale that I already have. So I'm going to say that my graph should go from 0 to 2 pi. Each of my boxes is pi 12ths because I used 12 boxes to make pi. At the very bottom of my graph, it looks like 3, 6, so I went to negative 3.33333 for the bottom and 3.33333 for the top. And then my y's went by 1/3. So I just set my graph up so that it looks exactly like this. And then when you graph it on your calculator, you can tell if it's accurate or not. And there we go.